Today we discuss Riemannian manifolds. So what is a Riemannian manifold? Up to this point in our course, we've studied topological spaces called smooth manifolds, topological manifolds with smooth structure. Now today we are going to add an additional extra structure to our smooth manifolds called Riemannian metric. With this additional structure, with the Riemannian metric, we would get something called Riemannian manifold, and that's actually the space we can do geometry on. So in order to do differential geometry or do geometry even in the sense we learned from basic Euclidean geometry, we need this extra structure. To understand this better, think about two sphere, the standard round two sphere inside R3, right? We know this is a smooth manifold. But there is also another embedding of two sphere inside R3. We can embed a two sphere smoothly inside R3, but in this weird way. We can stretch it and push it and pull it so that it would look like this. This is still the two sphere. As smooth manifolds, these two things are the same. So they're the same as smooth manifolds. But well, when we look at them, we notice they're not really the same. The geometry on these spaces is not the same. One of them is round, the other one is stretched in a weird way. The curvature, the length of curves on them, totally different. If we pick 2 points P and Q on the two sphere on the left side, the geometry near P and near Q is completely identical. In some sense, the space is symmetric. That's not the same for the other two sphere. If I pick 2 points P and Q, geometry near P and near Q, they're completely different, right? So they are different as so-called Riemannian manifolds. There is something different about them. So today we are supposed to define what is a Riemannian metric on smooth manifolds, and we would say this allows us to do geometry. The essential things this would allow us to do is that first we can compute the angles. So if we have two vectors, two tangent vectors on our manifold, we can compute the angle theta between them. This allows us to compute length of curves. Suppose we have a smooth curve on the manifold, like the one we see, it allows us to compute the length of the curve. Also, using that, it allows us to compute distance between points. So for any 2 points P and Q on my manifold, I can say what is the distance between P and Q. So these are based on this notion of Riemannian metric. And all of these together are the fundamentals of geometry, right? Being able to compute length and angles, etc. We have to know these to do geometry. Okay, great. So let's get back to our, like always, let's get back to our model case, Euclidean spaces Rn. We do geometry on Rn, right? On plane R2 or R3. The way we do geometry on Rn is essentially comes from a notion of inner product on Rn. So let's review the standard inner product on Rn and see how that enables us to do geometry. So what is an inner product on Rn? Take two vectors u and v in Rn, right? Two vectors. So say each of them, say u would have n coordinates, u1 up to un. Each ui is a real number. Same for v equals v1 up to vn, n tuple of real numbers. We define the inner product of u and v, or sometimes called the dot product, the standard Euclidean inner product. Let's kind of emphasize on that. The standard inner product we know from, say, calculus. For two vectors, u and v is given by the following. So sometimes it's called dot product. It's denoted by u dot v. Sometimes it's denoted by this other notation. We can use parentheses, we can use left angle, right angle. Sometimes it's denoted as g of u and v. G is sometimes used for the inner product. To emphasize this is the standard inner product on Euclidean space, we might denote g with subscript e. Okay, this is essentially defined to be u1, v1 plus u2, v2 plus up to un, vn, right? So this is the definition, the standard definition of inner product. So it's sigma ui vi, where the index I goes from 1 to n, right? Okay, so this is our notion of inner product. Great. So in fact, this is one example of inner product. Let's maybe focus on a simple case where n is equal to 2. In this case, this would be u1 v1 plus u2 v2. This is the standard inner product, but there are some non-standard inner products we can define too. We haven't defined what really inner product is. In fact, the one we just defined is an example of a more general notion. There are other examples of inner product. So let's first look at another example, and then I would tell you what I mean by inner product. So I can define inner product of two vectors u and v to be 2u1 v1 plus 3u2 v2. So I change the coefficients from all of them being 1 to these kind of coefficients 2 and 3. This is another example of inner product. Before telling you what it means to be inner product, let me tell you something which is not an inner product. So if I define u dot v to be u1 u2 u1 v1 minus u2 v2, this is not an inner product. So what is an inner product? How is that I would call one of these a non-standard inner product and the other one not an inner product? How do we define the notion of inner product? So let's go to a bit more abstract kind of setup. In order to define inner product, we should have a vector space. Okay, so let's say V is a vector space. For the sake of our course, let's say it's a vector space over R, the field of real numbers. So the real inner product, or essentially inner product, is a product. So it takes two vectors. So you can think about it as a map from V times V, because you take two vectors as inputs, and the output should be a real number, right? There are three essential properties an inner product should satisfy. Any product which satisfies these three properties, I would call that an inner product. First, inner product of any vector by itself should be non-negative. For any vector u, the inner product of u with itself, or u dot u, should be greater than or equal to 0. And it should be equal to 0, u dot u, the inner product of u with u, should be 0 if and only if u is the vector 0. So this 0 is not the real number 0, it's the vector 0 in our vector space. That should be the only case. Any non-zero vector you pick, the inner product of u with itself should be positive. This property is called being positive definite. So an inner product must be positive definite. Okay, that's the first property. What is the second? The second property is that the inner product is symmetric. So the symmetry is the second property of the inner product, in the sense that inner product of u and v for any two vectors u and v should be equal to the inner product of v and u. The order should not matter. If I change the order of u and v, first u then v or first v then u, the value of the inner product should be the same. The third and final property is that it should be bilinear. What does it mean? It should be linear in each component. So if I pick three vectors, u, v, w, in my vector space, and say a real number c, I can consider the vector u plus cv, and look at its inner product with the third vector w. This should be equal to the inner product of u and w plus the real constant c inner product of v and w. Okay, so that's the third property. Same should hold for the second component. If I replace w with the sum of two vectors or scalar multiplication, same thing should hold. It follows from the symmetry. Okay, so let's get back to R2. The standard Euclidean inner product would be u1 v1 plus u2 v2. You can say it is positive definite in the sense that inner product of u with itself, u dot u, is u1 squared plus u2 squared. This is a non-negative number, and in fact it is equal to 0 if both u1 and u2 are 0, so the vector u is equal to 0, 0, right? The vector 0 in R2. The non-standard one we defined was 2u1 v1 plus 3u2 v2. Well, this is positive definite because with respect to this new inner product, the inner product of u with itself would be 2u1 squared plus 3u2 squared. Again, this is greater than or equal to 0, and it is 0 if and only if each one of these terms, u1 and u2, are 0. But the third inner product, not inner product, we define u1 v1 minus u2 v2. This is not positive definite. Think about the vector 1 and 2, right? The vector with components 1 and 2. U dot u would be equal to 1 squared minus 2 squared, right? This would be negative 3. This is a negative number, right? This is not a positive number. Therefore, this is not positive definite. Therefore, this is not an inner product, right? So for us, definition of inner product is being positive, definite, symmetric, and bilinear product on vector spaces. Okay, great. So going through these examples, we have like a basic understanding. It would be good for you to check. These are in fact symmetric and bilinear. Also note that I can rewrite the inner product in a slightly different way. I can write the inner product in a matrix multiplication form of u1, u2 times the identity matrix v1, v2. In the second case, u1, u2 times the matrix 2, 0, 0, 3, v1, v2, which is the transpose of v. We denote usually this matrix by G. This is the common notation. So the kind of inner product is like U, G, V transpose, right? So in fact, in Rn, the non-standard inner products can be given by the vector U times the matrix G times the V transpose, matrix multiplication of these. Being inner product implies this product should be positive definite. It implies the matrix G should be positive definite. So you might remember the definition of positive definite matrices from linear algebra. Essentially, it meant here the inner product of U with itself, which would be U, G, U transpose, should be non-negative, should be positive if U is non-zero. There's a different definition in terms of eigenvalues being positive. And the inner product must be symmetric. For the matrix, this translates to matrix being symmetric. So the kind of component on the ij position should be the same as the component on ji position. So G should be equal to G transpose as a matrix. And bilinearity just follows from the product kind of format of U, G, V transpose. You can check that. We don't need to add extra assumption on the matrix G. So G is an n by n matrix. With these two properties, any inner product is essentially given by this way. So all the information of inner product is kind of restored or saved in this matrix. Okay, great. So our inner product kind of gives us geometry. That's what we claimed. Why is that? So first note that if I have a vector in Rn, using inner product, let's denote inner product, it might be a non-standard inner product. Let's denote our inner product with this thing. With this notion, we can first compute the length of vectors, or the norm or modulus of vectors. So pick some u in Rn. The length of the vector u depends on what I define as inner product on that space. I define the length of the vector u to be the square root of inner product of u with itself. So if you change your definition of inner product, pick a non-standard inner product, the length of vectors would change. Also remember, I can, in kind of Euclidean geometry, we have inner product of u and v is equal to length of u, length of v, cosine of the angle between them. Now, if I have any non-standard inner product, I can use this to define what I call an angle between two vectors. If I have a notion of inner product, I know what is u dot v. I define that using my inner product. I know what is length of u, that's square root of u inner product u, and length of v, square root of v dot v. Using this equation, I leave this as an exercise to you. Using this equation, you can essentially decide what you would call an angle theta between two vectors. So if you pick a non-standard inner product, you get non-standard length and non-standard angle, which would be different with the standard one. Okay, great. So you see, inner product gives us the notion of length, gives us the notion of angles. That's essentially the foundation of geometry. Now we want to extend this notion of inner product of geometry and geometry from Euclidean spaces to smooth manifolds. That's the main goal of this lecture. How can we do that? Suppose I have some smooth manifold. Again, schematically, let's think about two-sphere. Let's say we want to do geometry on two-sphere or some arbitrary smooth manifold. So let's kind of sketch something here. Let's say this is our manifold. So I want to do geometry. I need kind of a notion of inner product. But you might say this is not a vector space. How would you do inner product? Or what does it mean? I want to be able to define inner product of any two tangent vectors u and v, tangent to the manifold at any point. So let's say u and v are two tangent vectors at some point. I want to define the inner product of u and v. So we want to have a notion of inner product on tangent spaces at different points. I want to be able to do that for vectors tangent at P, vectors tangent at Q, vectors tangent to any point, to the manifold at any point. That's the notion of Riemannian metric. Riemannian metric, usually denoted by G, is essentially a tensor, as we are going to see, such that to any point P in our manifold, if we look at the tangent space to our manifold at P, it assigns an inner product to that tangent space. So tangent space at any point is like a vector space, right? So it defines an inner product on tangent space of M at P for every P, right? U and V are in tangent space of P. Those two other vectors are in tangent space of M at Q. Riemannian metric is a notion of inner product everywhere, on every tangent space. So G of U and V is supposed to be the inner product of U and V. That's usually the notation. Sometimes to specify, it depends on the point P, we use the kind of subscript P. As we go around the manifold, this kind of inner product would be changing smoothly. And the kind of essential idea is that if you think about the standard two-sphere versus this weird stretched two-sphere, they're not the same as Riemannian manifolds. The notion of inner product, angles, lengths, distance, and these two manifolds are different. The geometry of these two manifolds are different. In that sense, they have different inner products. Right. Okay, let's say we have some, again, abstract manifold M. Let's pick a small open neighborhood U, and let's say we have local coordinates on this open neighborhood. So it's a chart, let's say x1 up to xm. So let's say x is a point in this open neighborhood. I want to be able to define inner product for any two tangent vectors u and v. So let's say x is a point in U, with this x1 to xn being the coordinates. Let's say u and v are two tangent vectors, tangent to m at the point x. So let's say these are u and v. So just as we discussed in the Euclidean setup, the inner product of these vectors, the inner product of the vectors at any point or on any vector space, can be written as the form of u times the matrix times v transpose. But now the matrix depends on the point x. The matrix G depends on what x we're picking. If I pick another point y, this matrix would change. If I pick z, this matrix would change. So this matrix is now like a function, which to any point inside U, it assigns a matrix. So it's a matrix valued function. If I define this matrix as denoted, its components with Gij, for ij being between 1 and m, each Gij is a real valued function on U, right? So we get an m by m matrix valued function, okay? So the point is that as we move x, G should change smoothly. Okay, great. So in local charts, we can kind of present our metric with a matrix. Okay. Again, let's say we have a manifold M. Let's say we have a point X in M. Let's say we have a tangent space. Now, to any tangent vector, we can assign its length, just the way we did in Euclidean setup. What is length of tangent vector u? It's the inner product of u with itself, but the inner product defined on the tangent space at x squared root of that, right? So now having an inner product on tangent space of manifold, I can compute length of tangent vectors. So inner product allows me to compute length of tangent vectors. It also, therefore, allows me to compute length of curves inside my manifold. What does that mean? So suppose I have my smooth manifold. Let's say M is a smooth manifold and gamma is a curve. So what is a curve? Curve is a smooth map, or say piecewise smooth map, from an interval a, b to m. So let's say this is M, and let's say this is the image of my curve, right? So what is length of this curve? How can I define length of curve? So in order to define this, let's say t is the variable in the domain. Let's say t, any point in the interval is denoted by t. T is the variable in the domain. So if I look at the derivative of gamma with respect to t, at each point, it's partial t of gamma. It's a vector tangent to the curve. So at any point t, derivative of gamma with respect to t is the vector, is kind of like the velocity vector, right? The vector tangent to the curve. This is the tangent vector. If I have a Riemannian metric on the manifold, I can compute the length of this tangent vector. So Riemannian metric allows us to compute length of tangent vectors. This is a tangent vector, so it makes sense to define what is the length of this. Now let's integrate this from a to b, integral of this real number now from a to b dt. This is what I call the length of a curve. So just to specify that again, length of a tangent vector is called inner product of the vector by itself, it's squared root. So here, the kind of inner product is defined with the use of Riemannian metric on the manifold. That's why now lengths of curves are defined. We can measure what is length of a curve on the manifold. And the essential thing is that this is a geometric concept. This is well defined. It means it's independent of the parametrization. If you think about a geometric curve on the manifold, there might be two different maps which would project to that. There might be two different parameterization of the same curve. There are different parameterizations of the same curve. So you can, for example, go along the same curve first slowly and then very fast, or you can go along the same curve very fast and then go slowly, right? The map gamma would change the way you parameterize the curve. Its derivative would change. But it's a good practice exercise to see the integral we define would not change. Okay. Now let's see how using a Riemannian metric we can define volume of regions inside a manifold. So for simplicity, let's say A is an open subset inside our manifold. What is the volume or m-dimensional volume of A? We need notion of Riemannian metric again to compute that. Let's go back to the case of R2. If I pick some open subset in R2, what is two-dimensional volume of that? Two-dimensional volume is just area. What is area of A? From calculus, we remember this was integral of 1 dx1 dx2 over A, or integral of 1 dx dy over A. If we think about R3 and pick some three-dimensional region inside R3, let's say that ball, what is the volume of that ball? Again, it's integral of 1 dx dy dz, or dx1 dx2 dx3 over A. There is kind of a similar thing in Euclidean, in Riemannian manifolds. The essential thing here is that dx1, dx2, dx3, say over R3, is called volume 4. We are integrating volume 4. Over an m-dimensional manifold with a Riemannian metric G, there is also a volume form. So think about matrix. Your matrix defines a matrix. Take the determinant of matrix and take square root of that. So this notation G stands for both our matrix and the matrix represent that. Take its determinant square root. Multiply that by dx1, wedge dx2, wedge up to dxm. This is the volume form associated to the metric G on the manifold. So this is denoted by volume G. So if we want to compute volume of a open subset or region inside our manifold, we should take integral of 1 times volume form over A. This is the definition of volume. So if I have some A manifold here and some A here, this is the way to compute the volume of that. If I think about standard two-sphere versus that weird two-sphere, the same set would stretch out in the other one, and the volume would be different because they have different geometries. So in order to define area and volume, etc., again, we need the notion of Riemannian metric. So remark, in the previous lecture, we learned about tensors, right? In fact, the Riemannian metric is an example of a tensor. Riemannian metric is a tensor. And it's a kind of special kind of tensor. It's not a 4. It takes two vectors, give you a real number. It's not a 2-4. It's not alternating. In fact, it's symmetric. So it's a map from Tm times Tm or Tm tensor Tm to R, and it's symmetric in its components. So it's a symmetric tensor. So just to kind of do a summary, we started with a smooth manifold. We equipped it with a Riemannian metric. We call this couple a Riemannian manifold. And now we can essentially do geometry on because we can compute angles and lengths and etc. So this is the essential thing to do in the rest of the course. Just a question to finish this lecture with. Start with the smooth manifold. Is there necessarily a Riemannian metric on a given smooth manifold? So starting with the manifold, do we necessarily have a Riemannian metric on that? And is it unique or there are many of them? Yeah, what do you think? So that's the question to close up this section with.